Okay, this is chapter 20, part B. This is separated from part A just because part A is rather long, but they're sort of intrinsically connected. So this section is on splitting fields. Technically splitting and splitting fields, but primarily on splitting fields. So the idea is this. So given some polynomial, some p of x in f of x, we know by the fundamental theorem of field theory that we can extend f to a larger field in which p has a root. So we know by the fundamental theorem of field theory we can extend f to a larger field E in which p of x has a root. Now, roots correspond to linear factors. This we know. So what this is saying is, in this E of x, in this bigger thing, the polynomial factors, or rather, we can take a linear factor out of the polynomial. Right, so we could do like p of x is, and then some linear factor, and then some residual stuff. And these guys will be in EX. So there's a looming question here, which, well, can we keep making E bigger? Because this Q will have a lower degree than P. So why can't we, or can we, simply keep going, extend further and further until we've factored P of x completely? So can we keep going? So extending, let's say, f further and further. Until we factored, let's say, factored p of x completely into linears. Like, it seems like the answer is obviously yes, like in an inductive sense. And the answer is really yes in an inductive sense. So but that's the big theorem that we want to get to. So before we discuss that, we'll just have a definition or two. So that are associated to all of this. So first definition. We'll say let E be an extension field of f, and little f of x will be in f adjoined x. And we'll say, and this be a non-constant polynomial. So then we say, so the first phrase is that we would say that f of x splits in E. So if we may write f of x equals a x minus a1 dot 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 x minus a n, with a in f and all of the ai's in E. So two notes before I give an example is the phrase splits in E is, I don't really like it. I think a better phrase might be splits in E of x. because when we think of it, the splitting as being sort of factoring, and so technically we would think like, well, it's factoring in e of x, but the phrase that's used is splits in e. But if you prefer, you can say splits in e of x or splits over e. Might be better, but in any case, they will mean the same thing. The second note is this a, right? So we up in this factorization up here, right there. We have this a, which is in f, and all the other a's, which are in e. That a is just there to basically saying that we can pull the leading coefficient out. It really doesn't make a difference. Most of the polynomials we look at will be have leading coefficient 1 anyway, so that's not a big deal. But that's just there for that. So you can sort of, if you want, just think, okay, all our polynomials have leading coefficient 1, and you can throw that out, and then no big deal. So next definition is associated to this. And sort of getting to the heart of this idea is given a field f and a polynomial in f of x, an extension field E of f is called a splitting field. This is a long phrase. The splitting field of f of x over f. If little f of x splits in E and doesn't split in any smaller subfield. So formally doesn't split in any subfield smaller than E containing f. In other words, basically a splitting field means that it's as small as you can go, right? Like it splits in that field, but you cannot shrink that field any further, right? So let me give you a really simple example. So for example, like consider nice easy polynomial f of x. You've seen this polynomial before. Equals x squared minus 2 in q adjoint x. Like it doesn't factor in qx, it doesn't split because I need to have a square root of 2. But however, I can go really, really big. We can say x squared minus 2 splits in c because I can factor it. Now you might say like, well, that was a little overzealous, right? Like included all of C and I didn't really need to go that crazy. So we can sort of bring it down a bit. It could be like, well, look, it splits in R. Same reason. It'd be like, well, okay, that's still a little overzealous. It'd be like, well, look, let's go down to Q adjoin the square root of 2. Right? This is the field consisting of A plus B root 2, where A and B are in Q, which is the same, of course, as Q parentheses root 2. Right? So it turns out that this is the smallest you can go. In other words, if you throw anything else out and still contain Q, you will not get to split F. So think about, so I'll say can't go smaller. Why not? Because I'm not being formal about that. But we'll say, and so Q bracket root 2 is a splitting field. For f of x over q. My little note here, before we cut to our first theorem, is that we've been using this phrase like is a splitting field, right? So you might wonder why the word is not the splitting field. So it turns out these are not unique. I'll give you an example. So for example, same polynomials above, So that polynomial also splits in qx mod the ideal generated by x squared minus 2. Right? So this is because of the, let's say by the fundamental theorem of field theory, because by that theorem, it has a root, therefore it has a linear factor, and it's degree 2. So if it has a linear factor, it factors completely. So it splits in there. In fact, this is also a splitting field. That may or may not be clear, so it's something to think about. In other words, we cannot go smaller with this. And then at this point, you might see something like, but wait, these two examples, right? We know that these are isomorphic. So you might say that I'm being a little disingenuous, right? Because what I'm saying is that the splitting fields are not unique, right? So this phrase, not unique. And you might say, and then I gave you two. I was like, well, here's one, and here's one. And you might say, well, look, but they're isomorphic, right? So I'm not saying that they're not isomorphic. I'm just saying they're not unique. In which case your follow-up question might be, well, if I have different splitting fields, must they be isomorphic? And then the answer turns out to be yes. But structurally they're the same in the sense of being isomorphic, but they're different in terms of, you know, what they actually are. This q root 2 is basically a bunch of complex numbers. This q adjoin x mod the ideal, this is a bunch of polynomial constructed cosets. So those are different but isomorphic. So two big theorems associated to this new definition. So the first theorem is on the existence of splitting fields. And so this kind of takes us back to the beginning, where it seemed reasonable that given a field, we could keep extending it to pick up more and more roots, more and more linear factors, and finally get a nice result. So this is sort of basically what this theorem says. In other words, it says, let f be a field, and f of x be in big F adjoined x. Again, well, let's be clear, let this be a non-constant polynomial. We always want to exclude these because they don't factor into products of linears. Not in any real sense. So then there exists a splitting field for little f of x over big F. So the proof, I'm not going to do the proof other than to say it should sort of make sense at this point, and it's inductive in nature, but informally what we do the following is use the fundamental theorem of field theory to find an extension field with root. The root gives you a linear factor. Factor it out, factor it. In other words, put f of x equal that linear factor times the rest. This is the rest. This will have smaller degree. And then keep going with g. In other words, extend further until we basically run out of nonlinear terms. And then we're done. Again, that's informal. The formal proof is in the notes, and you can check it if you want. But that's the basic idea. Now, this is not really good to do in practice, because if you think about what happens, how this fundamental theorem applies is you start with a field and you build an extension field which is a quotient field, right? You mod out by the ideal generated by a polynomial. So if you do that multiple times, you basically get like ideals on top of ideals and quotient fields on top of quotient fields, and it's a real like notational mess. It's a nightmare. So this is to be thought about very abstractly, that you can increase these fields to get splitting fields that you want. Then the final theorem that I'd like to give, which I'll give some examples to really make it clear, because it's sort of, maybe it's easier to see what's going on with this theorem. This is on uniqueness. Of course, up to isomorphism that we can probably see what's coming. So we'll say let f be a field, and f of x be in big F adjoined x. Then any two splitting fields for little f over big F are isomorphic. So again, I'm not going to prove this. The proof of this is actually even longer. It involves two lemmas. Again, it's in the notes. Please take a look if you're interested. But what I want to do is just go through some examples so you really see what's going on here. And the examples will have a lot of details that I'm going to omit, but I'll point out what I'm omitting so they're for you to think about. But these are just to sort of give you a big idea about the structure of these splitting fields and the fact that they exist and the fact that they're unique. So I'm going to clear the screen off so I can put the examples on. But just the the two things to keep in mind, that they exist. There's always a splitting field, and that they're unique. So if you come up with multiple ones, then they'll always be isomorphic. So the first example is it's an old friend. We've seen it before. Again, it's x squared minus 2 in q of x. So we know two things, or really three things, but they're sort of a different nature. So the first one is that q adjoined root 2, which is the same as q parentheses root 2, which is the same as a plus b root 2, a and b and q, that this guy is a splitting field for x squared minus 2 over q. And then in addition to that, we know that q adjoined x mod the ideal generated by x minus 2 is also a splitting field for x squared minus 2 over q. And thirdly is that we knew this already, but by the theorem we know these are isomorphic. But we also know that if I wrote down another one, no matter where it came from, it would also be other isomorphic. To both of these, to these two. So in other words, up to isomorphism, there is just one. So the second example is a little more tricky, but it's still interesting. So consider the polynomial x squared plus 1 in z3 adjoined x. So we haven't really looked at this as much as we're going to right now yet. So I just want to make a sort of a couple of points. We've seen this polynomial in this ring, in this field, but sort of dig into it a bit deeper. So it turns out if we look at the set Z3 adjoined I, which we need to be cautious, right? Like Z3 is not a subfield of the complex numbers. So I can't say I'm taking Z3 and I'm sort of picking up I in an extension field. That doesn't make sense. So what we're doing here is we're defining this as the set A plus BI, where A and B are in the integers, or in Z3 rather, right? This set is a field. Right? It is in fact an extension field of Z3. So there's a looming question here, can you prove it's a field? Shouldn't be obvious. How do you do it? It's only got 9 elements. And in fact, x squared plus 1 splits in here. This is because we can factor it. Because x squared plus 1 equals x plus I times x plus 2i. Now, for what it's worth, it might take you a second to do that calculation and see that that's actually true, keeping in mind the coefficients are in Z3, right? And both of these are in Z3 adjoined I adjoined X, which is completely horrendous notation, where this means polynomials with coefficients in Z3I, which is sort of rather humorous. Now, it also turns out that this is a splitting field. Again, not completely obvious. For x squared plus 1 over Z3. So I'll make a comment about which things you should look at in a second. But in addition, by the fundamental theorem of field theory, f of x splits because it's degree 2 and has a root, and therefore has a linear factor, and therefore factors completely in the extension field C3 adjoint X mod the ideal generated by x squared plus 1, where this thing looks like a plus bx, not quite done, plus the ideal, where a and b are in root 3. Or in Z mod 3 rather. And in fact, this extension field is also a splitting field. So thus we can say, similar to what we said before, is that these two extension fields are isomorphic. And again, any other would be as well. So before I make a final closing comment, in this second example, there are a few things that that you should think about because they're not at all really obvious. So in other words, you should check why is this thing right here a field. You should check why it's a splitting field. Like, this might take some work, so I'm not saying these things are obvious. And over here and down in this next example, why is this a splitting field? In other words, why in these two cases could we not go any smaller and still have this thing split? So the closing note I want to make is that this statement, let me circle it, right here. It's just something sort of not totally off topic, but something worth considering. So this statement may look familiar. It may remind you of when we do things like this. Something like this. Oh, that's a plus up here, sorry. Bam, right there. But it's important to keep in mind that this thing right here, this guy right here, is the same as this. That, let me just make it clear what I want to say. However, this thing, right, assumes that there exists a larger field C, in which, or at least to say it assumes is a bit inaccurate. Like when we did it, when we thought about Q adjoined I, we thought about the fact that there was a larger field C in which I exists. And we sort of thought about our intrinsic knowledge that Q was contained in C. This was sort of something we knew. Right? With the purple case, right, the one that I just labeled, this is not so obvious, right? Like we're not doing this because like we can't say that Z3 is inside C, right? Because it's not. Right? But we can say that Z3 is contained in C3I as long as we define this properly. Right? So it's sort of a little bit, there's a little nuance going in there. It's worth being aware of, but also it's really easy to get sloppy with notation and understanding what's going on. But if this final statement is a bit confusing, that's okay. The big picture of all of this is that splitting fields exist. What it means to split, splitting fields exist, and they are unique up to isomorphism. And that is the end of the chapter.